I should add something, and I thought that it has, but if not, then not. Then it will just be. Let me think about it. So at the moment, no. If I forgot that I didn't add it to it. But definitely Snello, and it's, as I said, it's not a hard homework, I think. I think that it's easier than homework 5. And definitely if you got a WebGL, at least a very basic under control, the math is quite easy. And let's go a bit into the math again. So I gave you Snell formula that essentially says you see here a ray of light that is very small in the video itself. You see a ray of light, everything, going from one volume, say air, into glass, going in the glass for a while, and then going from the glass outside again. And Snello tells us, as I mentioned, I think, many times in the class, look at theta and phi, depending on the medium coefficient of where you're coming from, say air, and the medium coefficient of where you're going to, say glass. Each one has its own coefficient. There is a change in the direction of the light, and what gives you this relationship is Snello. And Snello is what governs refraction, not reflection, refraction, all over the place, following this formula that sinus of incoming angle times the coefficient of the medium on the other side, so coming and take the coefficient from the inside, gives you the coefficient from the outside times sinus phi. What you want to do is, for example, is to know what is phi. Why? Because then one of the ways to generate it is I know what is phi. Let's take the normal at a point, and rotate it by phi degrees. And you can definitely do homework 6 using this formula, and nothing wrong with this. You just need to be careful about the direction of rotation, because you have the wave, the surface of the water. If that's the, and my ray comes, and this angle is theta, then one of the options is to just take the opposite side of the normal, and rotate by phi. Why it's a bit could be annoying? Because you might need to rotate it clockwise. You might need to rotate the normal clockwise or counterclockwise, depending on is the incoming ray coming from the left of the normal or coming from the right of the normal. Right? The same thing about it, if my ray would have come from here, then the normal is the same. Make sense? Here is my ray. The normal is still in the same direction. What happened to the normal after the direction? I need to rotate it by phi, but at this point, it would be in the opposite direction. And if you want to assume that the viewer is not necessarily above the pool, then you need to compute two directions. You need to either represent it in polar coordinates or do some other tweaks. If you want to go for the bonus where the viewer is not necessarily high above the pool. What simplifies our life is the following form of Snello. I already showed you this slide, but now I added explanation because this formula, when you look at it without this explanation, could be confusing. what I was saying. Here is the direction t. What is the direction t? It's why it's confusing because there are 3 n in this formula, and I didn't want to change this n to another letter, but you need to some attention to remember which n is which. So there is n non-boldface, and n non-boldface would mean the coefficient where the area is coming from. So n is a constant coefficient where the ray is coming from. If the ray is going from air into the water, then the constant coefficient will be 1. That's this n. There is nt, which is the constant, the medium coefficient where you're going to. If it's water, it will be n.7 or n.8. Water or glass. And finally, there is boldface n. Well, we write this formula, but using vector notation. Boldface n, which is a vector. What's nice about this formula is that you don't need to compute sinus and cosine directly. All you need to do is vector multiplication by constant, and oh yeah, also a square root. That's the most complicated part that you're doing. And to save you the time of copying it, all you see here are products of vectors, maybe multiplication by a constant, and then the square root. And I shared with you now the GeoGebra where I wrote all of it, and here is well the form, and you can just copy the formula directly from the GeoGebra. So implemented twice, once when the ray is going from air into the water. So that's D in the slide, the direction that it comes from. And T, you see that the edge moved a bit. It's not, it doesn't continue straight, it bends a bit. That's T, according to the formula. And of course, when we are going from the water back to the air, then the reflection is on the opposite side. And as a sanity check, if I reverse the direction of the ray, then it goes back to the viewer eye, which is essentially what happens in the pool. And it's right. So yeah. So I recommend just take the GeoGebra formula as is. A question for all of you. You see in this expression, that there is a square root of something, which is 1 minus some number, and this number could be larger than 1. So 1 minus this number will be negative, and now I want to ask for a square root of negative thing. So let's understand what happens when I'm close to this number. So right now, here is my surface of the water. Normal, the ray comes from the water, passing from the water to the air in the direction of the normal, and they continue in the same direction. So no effect of Snell law yet, but when I'm moving the source, say it's a lamp that you have in the bottom of your pool, I'm moving the viewer direction, and accordingly, Snell law does what it needs to do, bends the water, bends the light going out from the water by some angle, And then when you start to look at it from a gazing and gazing angle, the water is here, and I'm slowly moving my view. microphone not. Sorry, and the message goes into 16, so we lost lots of time today. Hot. Okay. Should always remember. Okay, now we have volume. Microphone lost battery. Sorry about it. Okay. For one particular direction, where my finger is, there is no object there. What should I do? What should I do at this particular pixel? More than one possible answers. But possibly there is a default color, which I'll use in this case. Possibly you put the environmental, sky, mountain, everything that is far away in the background. Everything that is far away, we had other images. Everything that is far away in the background, you're putting as a environmental map, either as a sphere or as 6 images, and we thought is that surrounds you. So you're just asking it which of these images this way is pointing to, but these 6 images, WebGL, one of its services, will tell you you don't need to actually have a loop that checks these 6. At least you as a user don't have to do it. Specifically, just tell me, here are your 6 images, and you'll call them the environmental mapping around me, and I'll do this part of fetching the sky, if you're looking at the sky, automatically from the right image out of the 6, from the right coordinates. So everything that is, and the assumption, everything on this environmental map is just far, far away from you. Okay, so that's about this part. Backface culling will help you a bit. Occlusion culling will help you a lot. Things that you don't see, no need to render in details. Done. And as a rule, backface culling is not nearly as effective as occlusion, where Forstorm is somewhere in between. Remind you what is backface culling? Well, if you want backface culling to work on, you have to tell WebGL, do use it, which you're doing by setting 1 bit in a set of parameters. In particular, you want to tell it, use backface culling. Give me an example where you don't want backface culling, I think. Need to think about it. Backface culling, just to remind you, look at, there is a triangle that you pushed, billboard that you pushed. Your processor will compute the 3 vertices. It will assume that if the 3 vertices appears in a counterclockwise order, which you do by the cross product, then this object is facing you and you want to show it. Otherwise, you don't want to show it because whatever it is, it's only the back side and the objects are fully around. Yeah. That's examples that I have in mind. Billboard, maybe you want to show it, but maybe you want to show different color from back and forth. To partially transparent object, definitely yes, that would be the case, that I would not use it. Otherwise, yes, because, you know, if it's triangle that you want to show, then it will start to think per pixel, what's the shading, what's the color, what's the texture. If it's triangles that I can ignore, quicker. Forstorm cooling, essentially you want to say, I specified the camera parameters in a few possible ways. You can specify the Forstorm by specifying one color of this pyramid, which would be, for example, near a lower and left one such color and opposite color, and the assumption is it. That gives you both camera allocation, angle of view, and so on. The camera here is assumed automatically that we'll see it right here, and this will be the angle of view, and everything will be done automatically. And now the algorithm says if I have a triangle that is fully outside the force-room, if somebody is feeling good enough in their pronunciation to tell me how to pronounce exactly force-room, because I know that I'm not there. Sorry? Yeah, but okay, yeah, force. I pronounce it as forced. Yeah. Not forced. Frustration. That's how it. Okay. Yeah. So triangle that is completely outside. Don't worry about it at all. All three vertices are outside the force room. Don't worry at all. Triangle that is partially inside, you want to find which part of the pixels fits it. Now, to compute if a pixel is above or below a plane, not that it's very hard, but it's somehow annoying, especially if you think about 90s, about implementing it in hardware. How can you make all these calculations faster? You want to use a matrix that will take this force-room. I think that I already forgot. We'll take this force-room, and these are your visibility rays, and we'll transform this force-room into an axis-aligned force-room. So this will be the z direction. This point will be mapped to some V1 will be mapped to V1 over here, V2 to V2, V3 to V3, and V4 into V4. And it simplifies the projection because now the depth of an object, the depth of a ray to this object, I don't need to worry anymore about the distance, and I don't want to call square root and to use Pythagoras. All I do is, for this particular pixel, I'll just compute the distance to the object. But based on only its z value. Now the distances are distorted, but they are all distorted, and the order is preserved. So object in the force room will move to other objects, but they are all linear transformation in the homogeneous coordinates. So what used to be a triangle stays a triangle, basically. And what used to be a straight edge stays a straight edge. And if two triangles, we discussed it, one triangle is closer to you than the other, then the distance when I measure the depth, what used to be closer to the viewer stays closer to the viewer. And an easier way to decide for this particular segment, S starts at P1 and ends at P2, each one of its pixels, I want to ask, is this in the force room or not? Which now becomes just a question in 2 dimensions. It will be just, is the y value of this pixel, is the y value of the pixel is larger than -1? Oh yeah, when I mentioned that it's a canonical force room, it also means that these corners would be in +-1, +-1, +-1, for all the coordinates in the ways that make sense. And the sides are orthogonal either to the z direction, to the y direction, z direction, or x directions. And now the deciding decision for every pixel, are you in the canonical form or not, is just becoming to look at its y value, smaller or larger than -1. Look at its x value, smaller or larger than -1, between 1 and -1. If it's between 1 and -1, it's x and y value, then it's in the canonical form, otherwise it's not. Okay, so by multiplying by one single transformation, complicated matrix, complicated to understand how it works, but once you calculated this matrix, or ask the hardware the software to calculate it for you, all the decisions making about the cutting the object, the clipping part, this part of the clipping happens very easily. Next, you can use a few trees that can help you get objects, some faster processing. They are not trying to replace a Z buffer, but they are trying to tell you there are things that are further away and things that are closer to you. They can be octree or quad tree that we are going to discuss quickly. They can be KD tree. They can be any hierarchy of bounding boxes. We'll talk about it more in the next meeting because I'm already 3 minutes late and I didn't even notice. Time flies. Yeah. Okay, how many of you took an algorithm course with me? Algorithm graphics? Just you. Okay, fine. There will be quad trees that I showed already. Some other objects, some other data structures that you are familiar with, but that's right. You'll see it again. We still have animations to go to, maybe not today, just to tell you about what's left in the course for sure. We have splines. Not students' favorite topic, but I'll have to give some splines, Bezier curves. We will have animations. Maybe we'll talk about gimbal lock, maybe not. It's a bit hard to understand how to get out of it. It's one word, kinematic, so definitely animation, quad space partitioning data structures for expedite calculation, more about rendering very large surfaces, splines, that's for sure. Maybe we'll have time to re-mention green screen, blue screen, how do I merge semi-transparent objects, and I have a few ideas of some fun topics to also mention, but I hope that we'll have time. Thanks. Thanks.